Sorry, everyone, I forgot to hit record. We're doing power series and we're doing this example, the top board, and we're just exploring it right now. And we're going to try to figure out sort of in general where it converges. So what about x equals 10? So now we get what, 7 to the n? What happens to these terms as n gets large? Yeah, right, because the terms are actually getting bigger and bigger. Right, again, you could rewrite this as 7/5 to the n. So the terms are not going to 0. So it diverges. That's the test for divergence, right? Okay, so this converges at like, what do we say, 4, 3, 0, but it diverges at 10. We could have tried negative values. It turns out that in general, if we want to like determine in general when this converges, we can use the ratio test. So to get some more information in general, or to get some more general information, because these were pretty hand wavy. I mean, you can give arguments for each of these, but at least, again, the ratio test is this powerful thing. We might as well, we have exponents. In fact, all of these power series always have like an x to the n. I mean, this one has x minus 3 quantity to the n, but it's going to have an nth powers in it. It's sort of like an infinite polynomial is another way to think about it. Like, even though when I erase like 1 plus x squared plus x cubed plus x to the fourth, it's like a polynomial that goes on forever. You can think of it that way. So, okay, so we have this sum. So this expression right here is a sub n, right? What is a sub n plus 1? Someone read off a sub n plus 1 to me. Anybody on the Zoom want to do it? I can hear you in my ears if you want. Afraid the people on Zoom on the spot. I never know when people on Zoom or if they're even listening. I have trouble watching Zoom lectures. I tune out a bunch. Let's see, Maggie. Yeah, right. We just replace n with n plus 1 everywhere we see it. Good. And now we want to do the ratio. So let's do the ratio test of this. And actually, here's going to be the time when it's good to remember that it's an absolute value. The ratio test says take the absolute value of the ratio of consecutive terms. So L is the limit as n goes to infinity, absolute value, a sub n plus 1 over a sub n. Here, let's see, the a sub n goes on top. Hopefully we've got used to the idea that we just flip the a sub n plus 1 upside down, right? Because we're dividing by it. And the thing you should be happy about is that there's a lot of cancellation, right? If you do this. Right, what do we, you start to see a lot of cancellation, right? With the x, we have one more x minus 3 on the bottom than on the top. We have one more 5 on top than on the bottom. And so I think we get something like this, right? did I do something wrong? Oh, what did I do wrong? I did everything upside down. I did an over an plus 1, not an plus 1 over an. I'm sorry. This is supposed to be, yeah, I knew I was supposed to know with the X on the bottom. Sorry about this. Oh my God. So I was supposed to put the ace of n plus 1 on top. So that was on top. I just got to jump down my throat when I do something like that. And then over ace of n, so that's the one that gets flipped over. Sorry about that. Okay, now the cancellation still works. It's just kind of upside, everything's upside down. That cancels that, that cancels that. And so we're left with x minus 3 over 5 times n over n plus 1, like that. Okay, I think that's better. Now, what happens with the absolute value? 5's positive, n's positive, n plus 1's positive. X minus 3, depending on x, could be positive or negative. So I think maybe you'll believe that I can actually just move the absolute value to here. Right, it's just the absolute value of that term that could be positive or negative. Everything else is positive, so it doesn't get affected. And then what happens to n over n plus 1 as n goes to infinity? Goes to 1, right? That just goes to 1. I could divide the top and bottom by n if I wanted to. There's actually a couple things you could do here. All of this here does not depend on n. So you could actually pull it outside the limit. And then I could also divide the top and bottom here. I just want to be a little more systematic about everything. Because right now that's infinity over infinity. So this is really absolute value of x minus 3 over 5 times the limit as n goes to infinity of 1 over 1 plus 1 over n. If I divide every term by n. And now that goes to 1. So we get just the absolute value of x minus 3 over 5. Okay. So this is what the ratio test spits out, is this expression. Absolute value of x minus 3 divided by 5. Yeah? Fun? What does that tell us? Anything? What does the ratio test tell us? Yeah. Then the series converges. Right. If the thing that gets spit out by the ratio test is less than 1, then the series converges, right? So this actually should help us if we can figure out what x is, make this less than 1. I'll write this down, give me a second. But that is the idea here, right? So the idea is just yeah, the idea is that, right, so x minus 3 over 5 is the output, absolute value of x minus 3 over 5 is the output of the ratio test. If less than 1, the series converges absolutely. If greater than 1, the series diverges. I'm just rewriting the ratio test right now. And if it equals 1, we get no information, right? Okay, so now we want to figure out, well, what we could do is that thing when I was plugging in values of x to the whole series, we could just start plugging them into this expression instead. Right, so now if I plug in 4, I get 1/5. And we saw that the series converged when x equals 4. If I plug in 3, we get 0, which is really, again, that center of convergence. If I plug in 0, we get -3, absolute value 3. We get 3/5, which is less than 1. If we plug in 10, we get 7/5, greater than 1. So all the stuff that we did before, all the examples we did before, it agrees with. So the idea is set this less than 1. And try to, and then solve for x, right? So now we're solving equations with absolute values. Fun. Fun. I love this stuff. So, okay, we can move the 5 up. We can multiply both sides by 5, right? And now there's various ways to interpret this. If an absolute value is less than 5, what does that mean about the actual number? What are the possible values? I told you the absolute value of blah is less than 5. What can you tell me about blah? Well, okay, well, you're getting way ahead of me. I'm just saying if the absolute value of blah is less than 5, what can you tell me about blah? Yeah. Yeah, you jumped a couple steps ahead, but right. So this expression is between -5 and 5. So there's this algebra way of saying like, well, this means -5 is less than x minus 3 is less than 5, right? I also like to think that there's a geometric way to think about this that I sort of prefer, which is that, let's just go over to a number line for a second. If I have a and b on the number line, what's the distance between a and b here? Someone say it. B minus a. But if I didn't tell you anything about a or b and I didn't draw them, b minus a, it could be b minus a, but it could also be, yeah, it could be a minus b if a happened to be on this side of b, it'd be a minus b. So in fact, the distance, the safest expression for the distance between 2 points on the number line is absolute value of a minus b, or b minus a, doesn't matter, right? Because if b is greater than a, or if b is less than a, it doesn't really matter what side a and b are. So another way, so you can do this sort of algebra way, or there's a geometry way of saying the distance from x to 3 is less than 5. And so if you draw that, here's 3. If I have like an x here, x could be anything, right? So the distance is less than 5. So that means I can go all the way over to 8, or I can go this way to what? This is probably what you said. -2, right? So I can do that and say, oh, here we go. It's like, it's really these ones that satisfy, it's these numbers that satisfy this, right? You can get that over here too, just by adding 3 to all 3 of these, all 3 sides of this, right? So if I add 3, I get -2 less than x less than 8. Adding 3 to all of those, right? So all of those, either way leads to the same conclusion. I just kind of like, I like thinking of that as a distance. You can kind of see it immediately. Okay, so go back to power series and think about when this converges. We also know it diverges when this is greater than 1, when this expression is greater than 1. And that would be the distance from x to 3 is greater than 5. Right, if I made this a greater than 1 instead, I can make this a greater than 5. And that would be the distance from x to 3 is greater than 5. So that's like out here. So that includes that 10 that we plugged in, right? So in here, it converges. Out here, it diverges. The series diverges. Out here, the series diverges. So what's the center of convergence? What did we say it was? 3. And now what's the radius? The radius is the distance from the center in each direction that it converges, which is 5, right? So R is 5. Okay, and the way it kind of works out usually when you do these is if you end up with a number down here, that's your radius, and then this is your distance, but you have to be a little careful. It's kind of nice to work it out. So radius equals 5. Okay. So now we know, do we know everywhere? Have we completely analyzed this within an inch of its life? We know every point for which the series converges or diverges. We know almost every point. We know if x is between -2 and 8, the series will converge. We know if x is bigger than 8 or less than -2, the series will diverge. What don't we know? Yeah, Maggie. Yeah, at 8 and at -2, because the ratio test would actually return equal to 1, right, at these 2 points, these 2 boundary points. So if we want the full interval of convergence, we have to actually analyze these 2 points separately. Okay, so yeah, there's a lot involved in this, but this is kind of just the idea of how this works. You just sort of like, you do the ratio test, you figure out the interval where it definitely converges, definitely diverges, but then at the boundary, you have to check. So let's actually do that. Because you can tell if x is, say, 8, right, and you plug it into that expression, right? If you plug 8 into the ratio test expression, then you get 8 minus 3, which is 5 over 5, which is 1. So you get no information. So, but x equals -2, x equals 8 give us no information. No info from the ratio test. The ratio test. Okay, so I have to check those separately. And that's kind of interesting because you actually can see what happens here. Like, there is something that the ratio test doesn't tell you. So let's try x equals 8, for example. I've now erased the original problem, but right, we have the sum x minus 3 to the n over n times 5 to the n. And if we plug in 8, you can sort of see how this is interesting when you plug in 8, right? Because you get 5 to the n over n times 5 to the n. Right, that actually gives you exactly something that cancels what's on the bottom. And so that's actually just the sum 1 over n, which is a familiar series. What does this series do? Diverges, right? So diverges. So this does not converge at x equals 8. What about x equals -2? Now we plug in -2 up here and we get -5 to the n. Now we have to think about this for a minute. You could write out some terms if you're not sure what's going to happen here. Right, you could write out the first few terms to see what's happening. But there really is a 5 to the n on the top and bottom, right? One thing you can do with this if you want to really see what's happening, is I can separate this -5 to the n as -1 to the n times 5 to the n. Right, -5 to the n can be rewritten as -5 times -5 is -1 times 5 times -1 times 5, which is -1 times -1 times 5 times 5. I just said numbers into the air. Who knows if people, but is that believable? So the 5 to the n's cancel again, and we get this series. Which does what? Yeah, this conditionally converges because its absolute version is the harmonic series which diverges. But this is your classic alternating series that bounces back and forth, and the bounces get smaller and smaller and go to 0. So this converges. The alternating harmonic series converges. Which converges. Okay, so we now have every point now. So I can draw this again. I could put 3 in the center, 8 over here, -2 over here. We actually get convergence at -2. So I'll fill this in. We get all this converges, but then we get an open circle right here because it doesn't converge there, right? And then it diverges outside of these values. So it's something like that. So the power series converges for -2 less than or equal to x, strictly less than 8. Right. Some books and stuff will also write this as for x in the half closed, half open interval. And some other countries, instead of using this, they use a bracket facing the other way. Have you seen, is that how you've seen it? Or that's how you do it? Yeah, I've international students have told me this, that like, it's like that to be not included. That's just a different, we use like, yeah, rounded parentheses for not included and square brackets for included, but then there's other notations. If you're not sure, just write this. Right, that's there. Okay, so yeah, anytime we have this, so this is kind of a step up, right? We have this extra like level of difficulty now where we added a variable in, and now we have an infinite number of infinite series for every possible value of x. And we've actually, but we can use the ratio test to analyze most of those values. And then we have these 2 boundary points we have to. So that was the radius was 5, the center was 3, and the interval, this is actually the interval of convergence. Okay. Okay. That was fun. That was one example that took like 40 minutes. Although we tried some specific values of x first, whereas when you see this now, you just jump right into the ratio test. But you'd have to write it kind of carefully, right? I guess yeah, like the stuff over here, you have to do kind of carefully. The stuff that I'm erasing right now. All right. What I basically want to do, I want to show you one more example. There's one nice example that's kind of famous. And then I just have some practice problems we can try. As a handout. So let's take a break for a couple minutes. I've got 12:28 on the clock. So let's take a break for 5 minutes. That clock is out of commission for some reason. Let's take a break. I'll pause the recording. Recording. Okay. All right, that was, we did that example. Maybe you think, what the hell are we doing? We're doing these weird abstract things now. I just decided I do want to give you some insight into why we care about all this stuff. So maybe just a few minutes as a preview of the Taylor series stuff. Yeah. So let me give you an example of power series. And I'll tell you why it's an interesting power series. So actually, hold on, I just thought of something. Yeah, okay. I'm gonna show you something in Mathematica in a second, but consider this power series. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. There's a pattern there, right? I'm doing even powers over even factorials, plus or minus. And it has an x in it, so it's a power series. I could write it in summation notation as follows. I think it's like this. Let's check me and see if this makes sense. Minus 1 to the n, x to the 2n over 2n factorial. So since we have to always, since this is only the even, we're only getting the evens, we have to use 2n instead of n in the expression. And I think I have the plus minuses correct. Is that fair? Does that look like I have the right summation notation? Okay, let me show you. Let me show you something on the screen. So let's actually plot partial sums of this series. E.g. 1, and then 1 minus x squared over 2 factorial, and then 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Right, like that. When I say partial sums, I mean stop. Right, don't write an infinite series, stop it, different place. Okay, let me share screen on the Zoom. Okay, so here's 1. That's 1, right? That's the first partial sum. Second partial sum, it's plotting this on Mathematica. So if I do 1 here, all right, that's fine. It's a downward facing parabola, 1 minus x squared over 2 factorial. Yeah. 2, 3, 4. These are really 5. So that 3 was really this one. Or no, 2 was, this was 1, this was 2. Because that's up to k equals 2. And so on. But let me actually play this like a movie. Oops. So these are what the partial sums are doing. Oh, I keep missing that. I want to stop it, right? I guess I could just go on. I'm never gonna get it. I'll slow it down. It's stitching together something here, right? Isn't this kind of crazy if you plot the partial sums of this? They're functions of x. They're polynomials. What? It looks like cosine, doesn't it? Sine would go through the origin. This looks like cosine. Maybe I should do like a negative 20 to 20 or something. Isn't it really stitching together and making cosine? Sort of looks like cosine. So this is kind of crazy. But it turns out that this infinite series equals cosine. So they trace out, they become better and better approximations of the cosine function. Better and better approximations of cosine x, not factorial. Excitement, not factorial. If I drop cosine in here, I can plot both. If I do it carefully. Nope, didn't do it carefully. Plot. Oh, let me try that. Okay, so here I actually put the cosine graph in. There it is, right? It really is like plotting. It really is the cosine graph. And it seems to get better and better, which is just crazy, right? Crazy. Yeah, it turns out this is a really important part of mathematics. If we zoom way in, maybe I'll zoom into like -1 to 1 or something. You'll actually see something where it's sort of not, no, you can't tell there, it's not perfect. Actually, if I do like 1 to 2, wait, hold on a sec. I want to like zoom in on this point. What is it about 1.55 to 1.57. Sorry. It turns out it's not perfect. That's dumb. Wait, what just happened? Oh, you can't even see what's going on there. All right, I'm being silly here. Actually, what I want to do is something like this, minus 0.001. I want to do this very close to the center point. It is centered at 0. Let's try this. Wait, what's happening here? Why can't I see anything? I'm doing something wrong. You know what? I shouldn't have even. Never mind. Sorry. I don't know why. Okay, there's another example I can use that I've used in the past. It's better for messing with this. I just realized I'm being sort of silly. Okay, so here it is again. Here, we'll just run this animation and so we can be happy. Okay, so it turns out that it's not exact. Like if you zoom in enough, you would actually see differences. Only in the limit does it become exact. Like as n goes to infinity. But have you ever asked yourself, how does a computer know what cosine of like 3 is, cosine of 2? Does it get out a protractor and a? and a compass and try to measure the angle and draw and figure out the size of the x coordinate. No, it's got to have some formula, right? And it turns out that this is the formula. Like, if you want to know what cosine of 2 is, or like something like that, right? I can ask, well, I can actually ask the Google search bar. It's probably better. Yeah, like just cosine of 2 radians. Seems to be minus 0.41614 something, right? But how does a computer know that? What a computer does is actually plugs 2 into this formula and then cuts it off somewhere. Because this is just multiplication. This is just addition, subtraction, multiplication, division. Computers can do all that really well. Cosine is weird, but computers can do the basic operations really well, right? So like if I plug in 2 here, like if I just try plugging in like 1 minus 2 squared divided by 2 factorial, which is just 2, plus 2 to the 4th over 4 factorial. What does that equal? Oh wait, I think I did that wrong. I think I needed to put like parentheses around things differently. Sorry. Or maybe it doesn't know. Oh no, that is right. Okay. So wait, this was minus 0.416. Okay. So that wasn't, let me do another term. Minus 2 to the 6th over 6 factorial. Minus 0.42. It's getting closer, right? Plus 2 to the 8th over 8 factorial. Sorry. You know what? I really should blow this all up. Ooh, that's getting good. Right? I'm just adding more and more terms. Minus 2 to the 10th over 10 factorial. Look at that. It's like 4-digit accuracy. Right? And so, and this is not hard for a computer to do. 416146, 416146. So this is like 6-digit accuracy. So if you wanted like 20-digit accuracy, you would probably not need more than about 20 terms of this. And again, this is something computers can do very quickly and well. And so that's actually what a computer does, is it computes a different formula. And that's called the Taylor series. And that's why these power series are important, because like you can actually really say cosine x equals this horrible thing. But this horrible thing is actually easier to compute if you stop after 100 terms or something like that. Okay, so that's kind of where a lot of this comes from. The other thing is, what is the radius of convergence? So like here, it may be worth thinking about, yeah, what is the radius of convergence in this case? What is, because I can show you, actually, let me show you the other example that I have here, which is this one. Oh, wait, sorry, let me do minus 2 to 2. And let's plot. I don't know. We don't need 10,000 terms. Okay, so this is remember for the we already saw another example of this for the geometric series, where it was the sum x to the n. We actually have a formula for this when it converges, right? It's a over 1 minus r. But here a is 1, r is x. So that's another example where an infinite series equals a nicely defined function. It's just we wouldn't necessarily need a calculator to tell us how to compute this. So it may not be useful to use the this, but we had that, but it only converged between -1 and 1, right? So what happens now if we try to plot? Here's what happens. Whoa, that didn't work. So here's what happens is it's good, but notice it's never good past -1 or really past 1. In fact, 1 over 1 minus x has a vertical asymptote at 1. So you're never going to get the function to trace that nicely. But do you see sort of what happens here is that it's like tracing, but it's only good between -1 and 1. It never gets good over here because this series doesn't converge. You can see how it just leaps away. It keeps leaping away no matter what. That makes sense? So, but where the cosine one, we actually saw it. It seemed to be getting better as wide as we wanted, right? Like the cosine one, right, was getting better and farther from the origin. So I'm claiming you can really see the radius of convergence in this example, that r equals 1 here. But what about this one? So let's do this. Let's do this as an example together. Because this is another good ratio test sort of example. I don't know, you should try it. That thing in the top right up there. That's what I want to apply the ratio test to try to figure out the radius of convergence. I do think this all of a sudden shows you why people care about infinite series, because they're using these Taylor series, and Taylor series are super important, come up everywhere in math. So for the radius of convergence of this guy, apply the ratio test with a sub n is -1 to the n times x to the 2n over 2n factorial. Okay. So a sub n plus 1, I think you might have had to do some this somewhere on the homework. You replace n with n plus 1 everywhere, right? So we get -1 to the n plus 1. We get x to the 2 times n plus 1, the quantity n plus 1, like that. Right, because we're just replacing n with n plus 1. And we get over 2 times n plus 1 factorial. So that's really 2n plus 2s is what those are. So I could write this as -1 to the n plus 1, x to the 2n plus 2 over 2n plus 2 factorial. It should make sense with consecutive terms up there, right? Like if I go from the x1 at 6 to the x1 at 8 term, the top of the screen. Oh wait, did I stop the share? No, I didn't stop the share, of course. Sorry, guys. You should yell in my ear when I don't do that. Okay, sorry. This is what I'm trying. Yeah. Okay, so right. If you go from the 6 to the x1 at 6 to x1 at 8 term, you can kind of see it here. Like when n is 3, you get x to the 6th, and here you get x to the 8th. And I'm on screen, which I don't like. Okay. Okay, so now we need to do the ratio. So we do the limit, then goes to infinity of I want you guys to do this for a minute. Try to do it for a couple minutes at your seats. You're gonna do this divided by that, which is the same thing as this times the reciprocal of that. We're gonna have a big absolute value everywhere. Here, I'll write it for you, but try to see what kind of cancellation you get. Let me actually put the n plus first one on top. So take a minute, talk to your neighbors, see if you can figure out how to cancel, how this simplifies. You could also do like the 8th term over the 6th term if you wanted there to see for a specific example. In fact, maybe I'll write that over here. That's what you would have, right? Sometimes that can be helpful to try to create the general thing. It's how one of the specific examples would cancel. Talk to your neighbors. Just doing this example. So does everybody agree that I'm just doing the n equals 3 case just to see how it would work if you're ever not sure, I mean, I know we want to let n go to infinity, but it's instructive, right? Absolute value makes the -1 go away. Absolute value really only cares about the x because x could be positive or negative. And do you agree this cancels like that? Factorial over factorial. So did you guys do the general? Again, the factorial does, I mean, the absolute value makes all this go away. Doesn't even care about the minus ones, right? So what are you left with? What people get? Yeah, 2n plus 2 versus 2n. There's 2 more x's on top. So we get absolute value of x squared, 2n factorial over 2n plus 2 factorial. And then what happens with that? So that's interesting, but it doesn't work here, right? You don't get 2 factorial, yeah. Yeah, it's worth maybe even coming back over here and thinking, yeah, this was 2n, right? That was 2n. That's actually 2n plus 1. And that's 2n plus 2. Kind of if you generalize. That's where the 2n plus 2 factorial. So right, so in fact, this has all the numbers 1 through 2n in it. This has all the numbers 1 through 2n plus 2, but then what you're saying is left over is 2n plus 1 and 2n plus 2, right? So this is really x squared. You could write it this way, 2n factorial on top. I think exactly what Jack said. If you could do that, right? You could think of 2n plus 2 factorial as 2n plus 2 times 2n plus 1 times 2n times the numbers 1 through 2n. And then those cancel. And so you get the limit as n goes to infinity, x squared over 2n plus 2 times 2n plus 1. What happens to this as n gets large? What's that? Well, the bottom is just absolute value of x squared. So the top, if you plug in any specific x, it's a specific number. In fact, I could, if I wanted to, pull that out of the limit because it doesn't depend on n. And now what is this? Now what's this limit? Pretty clear what that limit is, right? 0. So we actually get, this is a thing that's going to be kind of strange here, is we get 0. Again, not factorial because 0 factorial is 1, but 0 excited. We get 0. No matter what x is, we get 0. The ratio test spits out 0. In other words, this series always converges for all x. So in fact, it's like an infinite radius of convergence. So the series converges always. And we say that R is infinity. And actually that is borne out. I mean, of course, this is a very narrow window that we have in the, oh man, I was back on the screen, wasn't I? This is a very narrow window we have, but it seems to be tracing the cosine, whereas this one didn't. This one was stuck only between -1 and 1. So this is working. So it's kind of amazing. Not only is this like, does cosine x equal that crazy infinite series, but it actually equals it for all x. So it's kind of cool. Okay, so that's where we're headed. We'll do some practice problems maybe the first half next time, just to practice some of these power series. And then I'll probably start talking about Taylor polynomials before Thanksgiving break. So, which is basically the idea I just showed you, but we can get into that more deeply. So, all right, everyone. I think, like I said, my office hours are pushed back a little bit today because I have a meeting. Thank you, Angela. And everyone else, I'll stop the recording.